Okay, this is the second video of this lesson series, and we're going to talk about the heat, and I'm using the word heat here in place of enthalpy because I'm talking about reactions, the enthalpy of formation, of forming a new substance. Okay, you don't have a place to write this on your notes, that's okay, this is a review. In the last video, we talked about different enthalpies, the H for enthalpy, or different changes in enthalpy that we could measure, and really the different refers to the different types of reactions. We can measure melting of substances, and the enthalpy of melting of substances. That would be, for example, CO2, dry ice going from a solid to a liquid. If we wanted the enthalpy of freezing for carbon dioxide, it would be the opposite. It would be CO2 going from a liquid to a solid. And so if whatever the delta H for this would be the opposite negative sign in front of what it was for this. We can measure and put in a table, and then it becomes useful, the enthalpy necessary to vaporize a substance. Here, if we vaporize carbon dioxide from a liquid to a gas, it has a certain heat. We'll pretend that heat could be 6.7 kilojoules per mole. I made up that number. If we wanted to find out the enthalpy necessary to take this carbon dioxide and cool it off, condense it back down to a liquid, then what would be happening would be going from a gas to a liquid. And if it took this many joules to make it go from a liquid to a gas, the delta H for going from a gas to a liquid would be the opposite. It would be negative 6.7. Because this reaction is just the reverse of this one. So I'm listing these because these are things that have been measured by other scientists. They put them in a table, and then we can use them. For example, when we use Hess's law, we can use these equations when we're trying, if we need to figure out the enthalpy of reactions where these would add up to something else. Similarly, people have measured the enthalpies of combustion. Carbon dioxide doesn't combust, it actually puts out fires. It cannot, the oxidation number of carbon at +4 cannot go any higher. But propane combusts, and so people measure the heats of combustion, put them in tables, and then we can use that when we are, if we need to, when we're using Hess's law, when we add up the reactions and the enthalpies, or we can just use it. It's handy to have this in a table, then we don't have to go measure it in the lab. Now we're going to learn what's called the enthalpy of formation, which is the synthesis of something, and we're going to learn a special way to think about it. So you have in your notes under heat of formation the word heat of formation, and that means formation, when we're going to talk about it, means to make something from its basic elements. So this, I'm using heat here, but it could also, I'm really talking about the change in heat and really the change in enthalpy, because this is a reaction, and enthalpy is the heat involved in a chemical reaction. You can think of it that way. So the heat of formation we're going to specifically define as to make it, and it is the new thing, from its, I'm going to say constituent, that means basic, constituent, or what makes it up, basic elements. So what is the energy necessary to make something from its component, from its parts, from its element parts? You could say it that way as well. You could say from its element parts. And I'll give you an example. If we were going to make carbon dioxide from its element parts, and we wanted to know the enthalpy necessary to make carbon dioxide from its element parts, well, what are its element parts? One element is carbon, so it would be from carbon, and the other element is oxygen, so it would be from oxygen. Now, when we talk about this thing called heat of formation, what we mean is we're making it from its element parts, and we have to define what state are those elements in. Are they gases? Are they liquids? What are they? Because something in a gas state will have more energy than something in a liquid state. We define, for this particular type of enthalpy measurement, the element parts as being in their standard states. And I'm going to define that on the next slide, but right here I'm going to use an example. A standard state means the state that well, we're going to define standard state. It means what the element exists in at 1 atmosphere, and 25 degrees Celsius. We have to define the pressure and the temperature for something at its standard state. So carbon at 1 atmosphere and 25 degrees Celsius is a solid. Oxygen at 1 atmosphere and 25 degrees Celsius is a gas. So if we wanted to talk about the standard heat of formation, so now I'm going to put this word here. I put it up here. Standard heat of formation of carbon dioxide. We'd be talking about how to make it from its elements when its elements are in the standard state. And you can write down standard state means at 1 atmosphere and 25 degrees Celsius. That's in your notes. And its elements that make this up, the carbon and the oxygen, at 1 atmosphere and 25 degrees Celsius, I'm telling you, carbon is graphite. It is a solid, and it exists as something called graphite, which is what's in your pencils. Oxygen at 25 degrees Celsius is about room temperature. 1 atmosphere is about pressure at sea level, where we live, essentially. And oxygen is a gas. So if you took carbon and oxygen and got them to come together, rearrange, and make carbon dioxide, when carbon was graphite and oxygen was a gas, what would the energy of that be? We would call that its standard heat of formation. And the way we would write that, if we didn't want to write the word standard heat of formation, we would write delta H, we put an F for formation, we put CO2, and we use this little circle up here, like a little degree symbol. That means standard. That means the elements are in its standard state. So we've defined standard states. Oopsies, that's not good. Now you can't read it anymore. And we've defined the standard heat of formation. Let's rewrite the enthalpy of the standard enthalpy for formation definition on the next page. So here is the definition of our standard enthalpy of formation. It is the enthalpy change required to make a substance from its component elements when those elements are in their standard states. And we define standard state as what they would be at 25 degrees Celsius and 1 atmosphere. And the way we write standard enthalpy of formation, we write delta H, or that's change in enthalpy, F for formation, and a little 0 up here, a little degree symbol. That means, this means standard. That's what that little thing means. So I gave you the example to make CO2 in a gas from its component elements. The way that would have to be from carbon as a solid, because carbon at 25 and 1 degrees Celsius and 1 atmosphere is a solid, plus oxygen as a gas, because at 25 degrees Celsius and 1 atmosphere. So the energy needed for these two things to come together and make carbon dioxide would be called the standard enthalpy of formation of carbon dioxide. So let's do the sample exercise on almost the second to last page. So our sample exercise here says, for which of these reactions at 25 degrees Celsius does the enthalpy change represent a standard enthalpy of formation? For each that does not, what changes are needed to make an equation whose delta H is an enthalpy of formation? And the first one they give, this is the first example we have, 2 sodium as a solid plus 1/2 oxygen as a gas, 1/2 of a mole of oxygen as a gas, makes 1 mole of sodium oxide. And what they're asking, is this the correct equation, the correct way to write the standard formation of sodium oxide? Well, the sodium oxide, the standard formation equation, has to be written as if it's made from sodium and from oxygen, and they both have to be the way they would be at 25 degrees Celsius and 1 atmosphere. Here we have sodium as a solid, so all metals are solids except for mercury at room temperature and 1 atmosphere. So sodium would be a solid in its standard state. So this is the correct way to write it. Oxygen at 1 atmosphere and 25 degrees Celsius is a gas. We breathe oxygen. We're at 25 degrees, so it's a gas. So this is correct. So these are the elements in their standard states as they would have to come together to make sodium oxide, the solid. Your equation, your heat of formation equation has to be balanced, and this one is 2 sodiums, 2 sodiums. 1/2 O2 gives you 1 O. So this is correct. This is the correct way to write the equation for the standard the standard formation of sodium oxide. This equation would be the equation, and then you could look up the heat of formation of sodium oxide, and it would be related to this equation. You need to know the equations in case you're going to use the equation in Hess's law. Let's go to the next slide and check the next one. Okay, the next question gives us this equation: 2 potassium as a liquid plus 1 mole of chlorine as a gas forms 2 potassium chlorides. And they're asking, is this the correct equation for the standard formation of potassium chloride? I could put a little FKCl down here. And the standard heat of formation of potassium chloride you would actually look up in the table. This is the table at the back of the book I'm looking at right now electronically. Here we have potassium chloride. We'll look at these in the back of your book tomorrow. And this is the standard heat of formation in kilojoules per mole. So the standard heat of formation would be negative 435.9 kilojoules per mole. So I could write that here, negative 435.9 kilojoules per mole. What I'm trying to find out is this the correct way to write that equation of formation? So let's look. We have 2 potassiums as a liquid. Now, at room temp at 25 degrees Celsius and 1 atmosphere, is potassium a liquid? No! Potassium is a metal. All metals except mercury are solids at room temperature and at 25 degrees Celsius and 1 atmosphere. So this is not correct. That would have to be a solid. That's the change you'd have to make. Chlorine is a gas at 25 degrees Celsius and 1 atmosphere. So that's the only change you would have to make. Let's do the next one. Okay, here's the third one. And we have glucose, C6H12O6. Eventually you should learn that this is glucose. You don't have to know it right now. And this is decomposing to form 6 carbons that are diamond. They're in the diamond crystal lattice structure, not graphite. We're going to talk about lattice structure in our next unit of solids. And also 6 hydrogen gas 6 moles of hydrogen gas, 3 moles of oxygen gas. Well, the first thing you should recognize, this is decomposing. We are not making one thing here. We're not forming one thing. So this reaction needs to be reversed in order to be the formation of glucose. It's not the formation of carbon or hydrogen or oxygen. And we'll talk about why in a second. But these are 3 things. So the first thing we have to do is reverse this to get the formation of one thing, which would be the glucose. And we can look up, before I rewrite that, the heat of formation of glucose. Where's glucose? It's right here. I think this is glucose. Here's your negative 1,273.02 kilojoules per mole. So that is the standard heat of formation. It's exothermic for glucose is negative 1,273.02 kilojoules per mole. But we're trying to find out what equation matches this enthalpy change. So first thing we need to do is flip this around, definitely, so that it's actually forming something and not decomposing. So we'll take 6 carbons that are in the diamond form plus 6 hydrogen gas moles plus 3 oxygen moles, and oxygen is as a gas, making C6H12O6. This is balanced. Okay, so now we are making what we want to make. That's good. This is this is a formation or a synthesis reaction. Formation is a more specific definition than synthesis, because in formation you just make one thing from its elements. However, and hydrogen at 25 degrees Celsius in room temperature is a gas, so this is in its standard state. Oxygen at 25 degrees Celsius and 1 atmosphere is a gas, so this is in its standard state. But carbon, do we see diamonds lying around everywhere? No. In order to make a diamond structure of carbon, you have to be at the very, very deep in the earth. You have to be under tremendous amount of pressure. In its standard state, carbon, and this is maybe new to you, but you need to remember it, carbon is in the graphite structure. We're going to talk about the differences of these in our next unit. So this is not the standard state of carbon. If you didn't know this, doing a homework problem, you would look it up. It has to be graphite to be in its standard state. This now, the way it's written, is the equation for the formation of glucose, and it would be associated with this much energy being released. One more thing. We never, well, if we were to form, let's stop. The standard heats of formation of elements in their standard state, for example, the standard state of hydrogen as a gas, or oxygen as a gas, or carbon as a graphite solid. The standard heat of formation of these things we define by definition is 0, because we don't need to, they exist that way in the universe already. We don't need to do anything to make them in these states. So by definition, if someone asks you the standard heat of formation of an element in its standard state, it's going to be 0. It's the end of this video. We have one more coming.